can imagine with a name like that, people hear it once and they quickly go to the acronym, which is STAGE. It's also my pleasure to introduce the chairman of the Woodrow Wilson Center, Joseph Gildenhorn. He's the chairman of our board and has been for a period of time. But before formally introducing him, I just want to say a special thank you to him on behalf of the center for all that he did to free Hala Esfandiari, the woman, as you know, who was imprisoned in Iran. She runs our Middle Eastern program here. And behind the scenes, the chairman and our president, Lee Hamilton, really moved heaven and earth and eventually successful. So on behalf of the center, thank you, Mr. Chairman. President George W. Bush appointed Joe Gildenhorn chairman of the Wilson Center Board in 2002. And having provided great leadership, he was recently reappointed to a second term, much to our relief, I must say. He brought to this position a record of public service, philanthropic commitment, and real business success. He has served as the U.S. ambassador to Switzerland under the first President Bush. He has served and continues to serve on a number of volunteer boards and received a host of honors. I really could take half the panel's time should I go through the full list. He has gone from success in law, banking, and the world to the world of real estate development. You may see JBG around town rebuilding the city, and that's our chairman at work. He's about to take another leadership role as chairman of the Board of Trustees at the University of Maryland. Mr. Chairman, the floor is yours.
Thank you, Ken. Let me welcome Hala Esfandiari, who just walked in. Welcome home, Hala.
Thank you.
Let me add my own welcome on behalf of the Woodrow Wilson Center, and I'm very pleased that the inaugural event of our Wilson Center's Global Energy Initiative will highlight the work of the University of Maryland's Energy Research Center, commonly known as UMERC. But before I describe UMERC's program and introduce today's panel, I would like to tell all of you who are new to the Wilson Center, including those listening on our website, something about the center. The Woodrow Wilson Center was established by an act of Congress in 1968 as the nation's official living memorial to President Woodrow Wilson. As both a distinguished scholar and the only American president actually to have a PhD and a national leader, Wilson felt strongly that the scholar and the policymaker were engaged in a common enterprise. By congressional charter, the Wilson Center is a nonpartisan institute for advanced study and a neutral forum for open, serious, and informed dialogue. It brings preeminent thinkers to Washington for extended periods of time to interact with policymakers through a large number of programs and projects. The center seeks to separate the important from the inconsequential and to take a historical and broad perspective on national and international issues. The center features Dialogue, a radio and TV interview show, the Wilson Quarterly, which really is a must-read for academia, the Wilson Center's Press, and literally hundreds of meetings and seminars every year. Today is a perfect example of the Wilson Center's philosophy at work. We are featuring some of the key members of the University of Maryland's Energy Research Center, again known as UMERC. UMERC is a multidisciplinary initiative that is dedicated to advancing the frontiers of energy science and technology. It is truly a campus-wide effort and includes every department in the A. James Clark School of Engineering, the College of Agriculture, Chemistry, Computer Science, and Social Sciences, as well as the School of Public Policy. Energy is and will be the defining issue of the 21st century, with enormous implications for national security, climate change, and global economic development. The Wilson Center has long been active on the energy front, but really without a center-wide focus. Recently, the Center's Board of Trustees felt it was time for the Center to take the next step and form the Global Energy Initiative. And this effort will build on the Center's past energy work, which will help define the future direction of energy research and use. I want to give special thanks to Sandra Gerber, a valued board member who has taken the lead in creating the Global Energy Initiative here at the Wilson Center. Now it's my distinct pleasure to introduce our outstanding panel of energy experts from the University of Maryland. You have their more complete bios in front of you, so my introductions will be brief. First, let me introduce Professor Greg Jackson, who currently chairs the steering committee for the all-campus effort, and he may want to say a little bit more about UMERC. His own research focuses on combustion and new sources of energy for engines, including the development of fuel cells. We will also hear from Dr. Anthony Janettos, an expert on climate change, who will speak about his own research and work, which includes his responsibilities as director of the Joint Global Change Research Institute, a partnership between the Pacific Northwest National Laboratories and the University of Maryland. We will hear from Professor Steve Hutchison, who's working on a project seeking to discover how marine bacterium can help turn carbohydrates into a fuel that can power our engines. And he's currently on leave from the university and is presently CEO of Zematis, a firm specializing in enzymes that can turn biomass into usable fuel. And finally, we will hear from Dr. Timothy Goulden, who represents Maryland's Public Policy School. And he has a current research project that includes the application of economic geography and computational social sciences to key questions, such as the security implications of policy responses to climate change. This outstanding team from the University of Maryland represents a much larger group of top researchers back at the university who are helping to define this country and the world's energy future. As Ken said, on a personal note, as an alumnus of the University of Maryland and a trustee of the foundation, and I'm married to someone who also graduated from the university, I can't think of a better way of launching the Wilson Center's Global Energy Initiative than with today's distinguished guests from the University of Maryland. So now, thank you, and let me turn the program over to Ken.
Thank you, Mr. Chairman. We'll ask the distinguished panel to speak in the order in which they were introduced, and we'd like them to speak for about 10 minutes. This is often difficult for academics who usually have us captured for a 50-minute lecture, but they have made the extra sacrifice this morning. And then after they've spoken, we'll move right into the question and answers and discussions. And we particularly invited this audience and picked this size room so we can have a real, what the Wilson Center likes to call a dialogue of democracy. Professor Jackson.
Thank you, Kit, and thank you, Chairman Goldenhorn. If you don't mind, we're going to do a slight change. I was asked first to introduce UMERC and what we're doing at the university, and I will do that for about 3 or 4 minutes. And then we're actually going to let Tony Janetto speak about the big problem, and then I'll come back and talk some about one of the possible solutions in the portfolio of solutions that we're sort of all seeking to discover in our efforts to address this problem. So just want to give you a brief that is not the correct presentation. Apologies. I'm not an expert in power.
See, we're there.
Jacqueline, maybe we could get someone to help here.
So there we go. So I think it's going to fly now. So the University of Maryland Energy Research Center is a multidisciplinary effort, as Chairman Gildenhorn explained, and it was only recently established in the fall of 2006 after approximately a year-long study of faculty member primarily from the Clark School of Engineering at the university. Of course, engineers tend to like to think that we have all the solutions, which of course is a myth that we promulgate amongst ourselves. And we were quickly informed by higher-ups in the university that this would not work as a solution to addressing energy research problems. And of course, the center broadly expanded to include other departments that were very active in energy-related research. Not only technology-related research, but also research related to resource management, such for example, the Agricultural and Natural Resources School, as well as economics and public policy. And if the steering committee is any representation of what this problem looks like, it's a steering committee of about 10 faculty represent, I think, about 7 or 8 fields, to give you an example of the diversity in the center. What was our sort of big picture mission? I mean, in a certain sense, this problem is not just about science and technology, but the initial focus was to say, how are we going to push technology in order to look at issues related to alternative energy generation and storage? You say storage, what do you mean by storage? If you start to think about renewable energy sources, sustainability, you start to think about supplies of energy that are intermittent, such as solar power, such as wind power, and therefore the idea of storing energy is going to be necessary if those types of technologies become a larger fraction of our energy portfolio. Obviously, as has been stated, we're very interdisciplinary in our approach, and obviously we see ourselves being like the Woodrow Wilson Center located in D.C. We like to think of ourselves as being a participant in the discussions that go on around this town, and so we want to provide some leadership, at least in the terms of energy technology and policy research, and hopefully today will be a good example of that. I'm not going to go into the full presentation, but I just want to give you a flavor of what sort of activities we're doing. The university is not doing this simply with external funds, but actually it's put up some of its own resources to sort of get the center off the ground. So on top of the research that's already been ongoing in the university, some new projects were started, and this gives you an idea of sort of what kind of questions the university might be addressing. There's a couple of projects that have started up in 2 types of fuel cells, which I'll discuss briefly in a subsequent presentation. We're actually looking at solar-based hydrogen generation, and so this is the idea of making a transportation fuel from solar power. They're actually very different approaches, even though you can sum them up in those 4 words. There's also a project, actually Steve's work in creating ethanol from cellulosic material. That has also received some funds to expand that effort. And then there's also some areas research in thermoelectrics, which is a material to convert heat into electricity. We're in the process of hiring new faculty. Perhaps some of you know some scientists, some engineers that are interested in a faculty position. They're welcome to submit their resume. And we've just hired an expert in lithium-ion batteries, a form of energy storage, Chung-Cheng Wang, who's just joined the school this past month. One of the things that we like to do as faculty members is we like to have students that are free from contracts. And one of the things that we're trying to establish in the center, and we have actually some, but we're trying to expand this program as energy research fellowships, so that students can actually work outside of the box or the context that's placed upon us in terms of contracts that we get from various government agencies or industrial partners. And so this is a strong part of what we hope to do as a center. We have, and it also is webcast, a Transforming Energy lecture series. I list a couple of examples here of talks that were presented last year. The reason I list these particular talks is that I found these 2 to be particularly paradigm shifting, at least within my own mind, of sort of debunking predispositions that I had about certain energy systems. So both of these happen to be government employees, which I found interesting that was the case.
One is not a government employee. Umbrella is not government.
Well, okay, indirectly that's true. He's managed by Battelle. This is correct.
Still Uncle Sugar's
And we also have a large research collaboration with, actually, if you see that, you say the Petroleum Institute, you might scratch your head. That is an institute within the United Arab Emirates, and they are actually interested in thinking beyond oil themselves. Why? Well, they have different motivations than perhaps we do. Their motivation is they see themselves, the longer they keep their oil in the ground, the more value it is. And so they're trying to move away from petroleum-based energy supplies in their own economy in order to allow for their own economy to be sustainable long-term beyond the short-term oil supplies. And then the last thing is we've actually started a curriculum for graduate students. I will stop at this point and not actually present any more about the actual center and actually turn it over to Tony so that he can actually present the big picture of energy and climate.
Just stand over here. If I stand here, am I in anybody's way? Great. Can I have the next slide? As Greg said, what I'm going to do is talk about beginning to assess the future of energy and climate. I'm the director of the Joint Global Change Research Institute in College Park, where, as our chairman said, we are a joint institute between the Pacific Northwest National Laboratory and the university. So, let me no, I don't want that one to do that. There we go. Let me start first by setting some background for this challenge. This is what the atmospheric concentration of carbon dioxide has done over roughly the last 1,200 years or so. And before the Industrial Revolution, it was in a pattern that has basically been typical since during the interglacial period. It happily percolates around 280 to 290 parts per million by volume in the atmosphere until we started doing two things. And one was deforesting the earth for agriculture, and secondly was burning fossil fuels. Over about the last 150 or so years, these two activities have contributed roughly equal amounts to the extra CO2 that's in the atmosphere. We're now about 35% or so above the pre-industrial background. Over the last 50 to 100 years, burning fossil fuels by far dominates the equation. There is essentially no scientific uncertainty about this result. We've known where the extra CO2 comes from for about the last 50 years. It's easily documented actually in the isotopic composition of the extra CO2 in the atmosphere. And what is true for CO2 is true for a number of other gases, methane, nitrous oxide. As anthropogenic activities have increased and sources have increased, we've seen dramatic rises in those gases in the atmosphere. Turns out also to be the case for sulfate aerosols, and in this case also largely from burning coal during this century. This rise in greenhouse gases in the atmosphere is associated with a slow but now quite pronounced change in the Earth's physical climate system. The recent report from the Intergovernmental Panel on Climate Change is really quite clear about this. For the last century, the observed changes in the physical climate system are almost certainly, in the IPCC vernacular, due to the combination of human activities plus intrinsic natural variability. The warming that we've seen, the so far modest warming that we've seen over the past century, cannot be explained, simply cannot be explained without including the anthropogenic contribution to the greenhouse gas, the greenhouse effect. If we then begin to look both a long ways back and begin to think about what comes ahead, we get a picture like this. If we compare where we are now, or where we are in at the last round of IPCC, which is right around here, to about 1,000 years previous, we are certainly in one of the warmest periods, perhaps not the absolute warmest, and as you see, there's a lot of variation. But the future holds some peril. This is the range of, essentially the range of climate futures associated with the range of greenhouse gas emissions projections from the last round of IPCC. We are clearly marching off the map in a much older vernacular. So let's. And now it likes this slide so much it doesn't want to go anywhere. So how do we begin to think about this? And one way of doing this, which is really kind of where our institute is using a discipline called integrated assessment research, a series of models and data analyses that are relevant to understanding the scale and timing of the drivers of climate change over this period of multiple decades to a century. And the traditional focus is really what are the potential long-term future emissions trajectories of the fossil fuel emissions, CO2, CO2 emissions from land use change, the non-CO2 greenhouse gases, and other chemically active gases, which are important for the greenhouse effect, and aerosols, which are important for the forcing in the opposite direction, for their cooling effect. And secondly, what would stabilizing radiative forcing, what would stabilizing concentrations in the atmosphere actually imply for the energy system and the climate system? The second role of integrated assessment is to bring the pieces of this climate research together in a way that can provide insights that would not otherwise be available. And I'm going to show you a couple of examples of that from the pursuit of single disciplinary research. I want to re-emphasize this interdisciplinary nature that Greg brought up just a few minutes ago. In principle, this means being able to understand everything from emissions to climate impacts and responses with everything in between. In practice, of course, this is a very tall order. And it does mean, in fact, pulling together a lot of state-of-the-art science and trying to understand its implications and representing more than one climate sensitivity, more than one area of uncertainty in our knowledge, which is extremely important. So let's talk a little bit about how some of these results begin to play out. This is a picture of what it would mean in terms of emissions, carbon emissions, in billions of metric tons per year to stabilize at a set of different concentrations. So this black area from about 1850 to 2000 is the historical record. This red is what we've called a reference case, which has some technological evolution in it, some changes in end-use efficiency, and so on, but has no implication that there's any policy decision to stabilize greenhouse gases. Pay attention to the time scale. This is 2050, 2100, 2150, etc. The reference case is essentially a continued increase in emissions and therefore, of course, in concentrations. Each of these lines is a scenario in which we have chosen to stabilize concentrations at a particular level. 750 parts per million. Recall that today's concentrations of CO2 in the atmosphere are about 390 parts per million. This is 650 parts per million, 550 parts per million, and 450 parts per million. A couple of observations. One is that stabilizing concentrations is not at all the same problem as stabilizing emissions. In order to stabilize concentrations, emissions have to peak and then they decline, essentially forever. And at some point they have to go to zero. Secondly, where the emissions would peak in order to stabilize concentrations anywhere, and how rapid the decline would have to be, is clearly a function of the stabilization scenario that one selects. And so a 750, to stabilize a 750 parts per million by 2300, as in this case, implies that emissions would peak somewhere around the end of this century, and then they would decline over a couple of hundred years, stabilizing at 450 parts per million is a very tall order. Emissions essentially have to peak in the next decade or two and then decline really quite rapidly for this. The third point is that selecting a concentration target is essentially the same as establishing a budget. It establishes, if you will, an allowable emissions budget that you then have to manage globally, because the world doesn't care, the atmosphere doesn't care where these emissions come from. And the stringency, these actually are for stabilizing at 2100. The budgets that you establish for stabilizing at any particular concentration vary from about 1,200 gigatons of carbon for the 750 parts per million case to about 480 gigatons of carbon in the 450 parts per million case. And aligned with that is what would happen if you did this by economic means. These measures imply a price on carbon, and as not surprisingly, for the less stringent scenarios, this is the 750 parts per million line, this price of carbon starts low and pretty much stays low. This is dollars per metric ton of carbon, not of CO2. And for the 450 parts per million case, the price starts low and increases fairly rapidly. All scenarios have this feature. Prices start low and they rise inexorably. And the reason is really quite simple. As you eat away at that allowable budget, you have less and less of it remaining. Therefore, the emissions that you are, in a sense, allowed to do and still meet the concentration target that you've set become more and more valuable. The models that we use to try to analyze these kinds of phenomena are comprehensive in the sense that they treat human systems, the energy system, agriculture, livestock, and forestry, and so forth. They generate emissions, which are then processed in a module on atmospheres and oceans, and then that's translated back to ecosystem effects. They are global in nature, but at least the economic portions treats different regions of the world. And we've taken a particular look at the role of energy technology. Because the challenge is, how can you begin to affect such a large and persistent problem? And one of the major levers that you have is the development and the deployment of energy technologies. And so that's been a major research effort of ours. And we have looked now in a report that we released just last spring, particularly hard at CO2 capture and storage, at biotechnology issues, nuclear energy, hydrogen systems, wind and solar, and end-use energy technologies, all of which I think you'll hear about more. We've also begun the challenge of intercomparing different integrated assessment models, our own, which is the Minicam model, a separate model from MIT, and a model from EPRI, and a model in a comparison program. But as much as we have looked at this mitigation question, what will we do about emissions? It has now become very clear that that's not the only response that we have to be thinking about. Because the fact is that if somehow emissions magically went to zero tomorrow, we would still have somewhere between a half a degree and a degree of change in global annual average temperature out through at least the middle to the end of this century. And we are beginning to see changes, climate impacts occurring now. It's really quite well documented. So as we speak, people are in fact beginning to adapt to climate change impacts. And this is now, I think, beginning to be recognized as part of a policy portfolio or a portfolio of policy responses. This ups the ante for information requirements. We now need knowledge of regional climate changes, of environmental consequences. We need information on what people are currently doing, how much does it cost, how effective is it, and it requires some ability to model this effectiveness of adaptation strategies as part of an integrated response portfolio. Nobody does this particularly well yet, and that's where one of the research frontiers is. Just as an illustration of the magnitude of the challenge, this is one picture. These photos are actually thanks to the National Park Service. They're taken from the same spot, Muir Glacier in Alaska. Well, the lake formerly known as Muir Glacier in Alaska. This kind of picture is repeated around the world, and we've even got the emergence of new phenomena about which we know relatively little. This is the revenge of freshman chemistry. Many of us probably took this course, that the surface layers of the ocean come into equilibrium with the partial pressure of carbon dioxide in the atmosphere very, very quickly. And as all of us, it turns out that what all of us were taught, which is the ocean is big enough that you don't have to worry about this, is wrong. The ocean has lost about 1/10 of a pH unit over the last 50 years and is likely to lose another 1/10 of a pH unit. We have never seen a change in ocean chemistry this large, this fast. And since the reactions by which corals extract calcium carbonate and other organisms extract calcium carbonate out of the water to build their external skeletons are all pH dependent, the consequences of this kind of a change, of the increase in ocean acidity, are at least potentially very large. Nobody imagines that they're good. So, a substantial complication is what if this change is not continuous, but if impacts are rapid or discontinuous, and we're beginning to look at this question. So for an analytical context, we have to begin to understand what's our capacity to adapt to change or to manage, in particular, threshold changes, what kinds of monitoring and predictive capacities do we need, and how do we mitigate those stresses so that we don't go through such tipping points. So let me finish up. We have a very real issue with challenges right now. It's a long-term strategic issue. Energy technology is one of the big levers that we have for mitigation of emissions, but coping with impacts will be another part of the story. Technology investment, development, and deployment is enormously important, in part because of the long-lived nature of the energy infrastructure. It's not like one can wait for 20 or 30 years to begin developing the technology. That has to happen now in order for it to actually be deployed in a way and at a scale that is commensurate with the scale of the problem. And we must begin to understand the nature of rapid change. Rapid change both in the climate system and in the parts of natural resources and ecosystems that it impacts. Thank you.
So I'll take the stage again and talk about one of these many possible technologies, and I'll try to keep it brief. I myself do a lot of research in fuel cells, and to many of you that immediately conjures up the idea of hydrogen as a fuel. And I like the subtitle talks that I give about fuel cells as seeing beyond the press releases, because there have been times in my research career where I felt that's what the fuel cell industry was good at producing, was press releases. So hopefully we can get beyond that. I just want to real quick throw up this, since Tony's already covered this, I think that I will not speak too much on this. And that is, if you think about sustainable energy systems, what are some of the questions that they have to, or challenges that they have to address? And I've listed them here, and what are some of the answers? And I think that, this suite of answers, first of all, they're interconnected, and second of all, they're not. None of them are significantly outweigh the importance of all the others. In other words, I think that the challenge will be, how do we bring these all to the table in a wise and intelligent manner? Hydrogen is listed there at the bottom, but it's in some ways it's a little bit different from the others, and that is this, that hydrogen really isn't an energy source. It's really an energy vector, an energy carrier. It's a fuel that we can take from place to place. And probably actually the energy vector that it's actually the most closely related to in terms of how it would behave is actually electricity. Unlike electricity, it's likely that hydrogen can be stored relatively easily. There are some people who might debate that with me. Unlike hydrocarbons, when we actually have hydrogen as a local fuel source, it doesn't lead to the CO2 emissions. That doesn't necessarily mean that it's a global CO2 neutral fuel. It depends on how we make the hydrogen. And we'll discuss that. So in general, when we thought about hydrogen, it's generally tied to fuel cells. That's partly correct. That's partly not completely correct. But I would say this, once something makes the State of the Union as a topic, a technology topic, it immediately becomes controversial. It doesn't matter who's in power or why, it's going to be controversial. And I think that that has become the case with hydrogen and fuel cells in general. There are basically, the reason hydrogen and fuel cells are linked is that the type of fuel cell that is being contemplated for automobiles, known as a proton exchange membrane fuel cell, basically requires high purity hydrogen to sort of provide the kind of power densities that you might need to put under the hood of your vehicle. And so, therefore, fuel cells and hydrogen are wed together. Of course, there are companies, actually more than just BMW and Ford, that actually are considering hydrogen internal combustion engines. So why not? We already have that technology. If we want to get rid of CO2 emissions, there might be an easier way. One of the things that if you talk to the General Motors executives and so forth, why they like hydrogen and why have they invested over $1 billion in fuel cell research. And the reason is not just that they like fuel cells. I'm not sure that they really do like fuel cells, but they actually like the idea of taking the environmental problem out of their backyard and out of their plants. And one of the nice things about hydrogen too, beyond that, is that hydrogen actually can be produced from a lot of sources. It can be produced from fossil fuels. It can be coal, natural gas. It can be produced from splitting water. And there's actually also thermochemical cycles that can be tied into nuclear plants that the DOE and a few universities are doing research on. If you think about, people are sort of afraid of a hydrogen infrastructure. It does exist today. In the U.S., actually, we make about 9 million tons per year. And that number has been growing. You think, oh, wow, that sounds like a lot. Actually, it's really not. If you think about our annual oil consumption, in terms of an energy equivalent, that's about 0.3% of our energy consumption in terms of petroleum based fuels. And the sad thing is that over 90% of that hydrogen is actually produced from a fossil fuel itself. It's actually produced from reacting steam with methane or natural gas to make the hydrogen. And that actually is a carbon-producing process, a carbon dioxide-producing process. It still has its advantages. And the primary use for hydrogen is actually ammonia, which is primarily for fertilizers, and also for actually improving petroleum products. So not very promising, at least in terms of what we're using it for. So here's where we are today if you want to think about how we would make hydrogen. And basically, it involves taking a natural gas fuel supply. You do it through a high-temperature process that adds heat, requires heat. That actually will release some carbon dioxide. You have to have a cleanup process. You try to store the hydrogen, and then in the end, hopefully, we think about a fuel cell. If you think about this is sort of like a full energy cycle process, going from the well all the way to the wheel of your car, if you think of this as a fuel cell for an automobile. You ask yourself, is that a good idea? And actually, if you think about overall well-to-wheel efficiencies, they're basically comparable to current-day hybrid vehicles. And in fact, if you start thinking about diesel hybrids, which are starting to become more and more part of the discussion of the automobile manufacturers, actually those would surpass the efficiency of a cycle like this with current-day fuel cell technology. And you think, well, why even bother? And that is, this of course is implying nothing about CO2 emissions. If you actually really want to value greenhouse gas emissions, this process actually is even still better than diesel hybrids, or by quite a bit. So I guess it depends on what you want to put your priorities in. If you want to put it on efficiency, probably we should stay with the existing infrastructure. and focus on diesel hybrids. If we want to place a high price on greenhouse gas emissions, then maybe even this preliminary process might be worth adopting, and pushing the technology that's needed for a future sustainable hydrogen infrastructure. What might that look like? I'll come to that question in a second. Just real quick about economics. I'm an engineering professor, and I tend to shy away from economics as much as I can, but then I'm always told that the primary problem with fuel cells is they're too expensive, so I have to at least sort of keep an eye on those issues. It's good to look at hydrogen fueling and just sort of to look at an idea. Several people have done studies on this. I think probably one of the more realistic studies was done by Shell, who's actually probably one of the world's leaders in trying to develop hydrogen fueling technology, and they estimated that for the U.S. to convert for 25% conversion of our fueling stations to hydrogen-based fueling stations, that it would cost about $19 billion. And my first reaction to that is that's not that much money compared to things considering other expenditures that our government has.
One quarter profits for Shell.
Yeah, this is also true. There are challenges with doing something like that. And there's an alternative idea that's promoted by some people. Is rather than thinking about going with these centralized fueling stations and maybe having to have hydrogen pipelines throughout urban networks, which some people are very frightened of, what about having your own fueling station at home? This also creates its own safety concerns. But if you could imagine, if we had an increase in our electrical supply, you could imagine having your own hydrogen fueling station in your backyard, for example. And the economics for that are still remaining uncertain. This is an adaptation from John Turner's slide. This is just getting back to the point that hydrogen actually can come from a lot of sources. This slide here in particular is actually focused on solar energy, but if you think about solar energy, it actually can be used in many ways. We can have photovoltaics, or we can use it, as Steve will talk about, to grow biomass, and we can use various conversion processes to produce hydrogen. So in that sense, it's very attractive because if you think about a suite of approaches to making your fueling source, you're not dependent upon a single supplier, much like we are somewhat today in terms of petroleum-based transportation infrastructure. If you think about what that might look like, it raises some questions. Okay, here's, for example, a scenario where you think about making electricity in a renewable manner, and you have some conversion, and then you have this electrolysis process that splits water with the electricity. The problem with that is, well, this process is about 25% energy efficient. So it's actually not particularly very attractive. However, when you think about the abundance of solar energy, particularly, maybe it's not such a bad thing. Maybe energy efficiency isn't the metric we should use to measure this type of a process. The other challenge is if we start to think about producing hydrogen on relatively large scales, either through renewable sources or nuclear sources, we have to start thinking about storing it on large scales. Well, hydrogen being a very light molecule, that's somewhat of a challenge, and I think that that's a question that remains unanswered. So I've implied that fuel cells are sort of linked to hydrogen, and I would like to sort of both accept that and then actually somewhat debunk it a little bit. Basically, there's two types of fuel cell technologies going forward, and I'm not going to get into all the details because of time. I'm certainly available today for people to ask questions. One is the proton exchange membrane fuel cell. The key things to be noted, this is the fuel cell that's being developed for automobiles. If you see, that's a real picture. That's Ballard Power Systems 85 kilowatt fuel cell stack. If you know anything about the size of the engine in your car, this would work very nicely for powering most vehicles on the road today. It does exist. It has a few challenges that remain. The primary one being cost. Okay? And that is actually a technical challenge. It's not just an economic challenge. It's about how do we reduce the cost. Because of this being the fuel cell for automobiles, it's received all the attention, both in terms of research development over the last 10 to 12 years, as well as in terms of the press that's covered usually in places like the Washington Post and so forth. There is another type of fuel cell that shouldn't be forgotten, and that's also it's called solid oxide fuel cells. it's actually primarily, it's a higher temperature beast. It relies on things like ceramics, and so it's not very good for thinking about driving down the highway and being going over potholes and so forth. But it actually is very significant. One of the significances of solid oxide fuel cells is that it's actually a very useful power plant for sequestering carbon. Because what it does is it pulls the oxygen out of the air and makes you a relatively pure CO2 stream that you could then easily dump into the ground that's not diluted by all the nitrogen in the air. Its primary application is more for stationary power, also maybe for distributed power. One of the things that people have discussed a lot is the idea of decentralizing power production. And there's security reasons for doing that, obviously. And the other challenge is that if you distribute power production, you can start to use the waste heat from these processes to do things that require heat. And so that actually improves your sort of energy utilization. If you notice that I gave, rather than giving I gave a schematic of a solid oxide fuel cell, and that's sort of indicative of where the technology is at. It does exist, but commercially it's not as ready today as PEM fuel cells. So I real quick want to just cover a couple of points about PEM fuel cells. If you think about costs right to today, and you think about where we are, a proton exchange membrane fuel cell right now runs at about 75 to 100 kilowatts if we're thinking about mass producing them. One of the leaders in fuel cell technology development actually works with us at the University of Maryland is Ballard Power Systems. Their primary base is Vancouver, Canada. They also have offices here in the U.S. And this is their sort of roadmap for cost reduction. Unfortunately, it doesn't come up so clearly. Right now, they're in the $80 range today, $80 per kilowatt. And you can do the math, 80 times 85 kilowatts is about $7,000, which is too much for the cost of an engine if you think about the total cost of a vehicle. But there is progress. And this, the time frames here is on the order of, these dots are on the order of 3 to 4 years separated. And they have a plan, and most fuel cell manufacturers are moving toward reaching a goal of approximately $35 a kilowatt. What will that take? And their goal is to do that. Currently, the thought about DOE is that we would consider the adaptation of a large-scale hydrogen infrastructure at 2015. That's sort of a decision date. We'll see if politics allows that to continue to remain as it is, or if it gets changed. We'll see that. That being said, there are markets today that are available for fuel cells, and I list a few there. What are the barriers? Why don't you have a fuel cell car today? And I think the biggest one is cost. And the reason that PEM fuel cells are so expensive is that they require a precious metal catalyst. And the polymer membrane that's used to separate the fuel from the air and then over which the fuel that actually is the heart of the fuel cell is also relatively expensive. The other challenge is that really this currently in today's technology, it requires a very pure hydrogen supply. That's not necessarily a bad thing, but it's certainly a significant barrier to where we are today in terms of how we get our hydrogen, which largely comes from natural gas and therefore is impure and requires a very expensive purification step. There are a few other systems level issues that are easily, I think, addressed. In fact, are being addressed every year. Improvements in these systems level issues are being tackled. And I list some forward solutions because of time. I'll pass over that. If you think about the high temperature solid oxide fuel cell, they're actually quite a bit more expensive. However, if you think about them for a stationary power source or a distributed power source, that might not necessarily be such a bad thing. The reason they're expensive is primarily due to materials fabrication. They actually don't rely on precious metals, but it takes a lot of energy to produce them. However, the solid oxide fuel cells, the proposed sort of power plants that are being developed at National Energy Technology Laboratories, have higher efficiencies than anything on the market today in terms of power plant efficiencies. And so, while the baseline costs might be high, the operational costs in terms of fuel, in terms of would be dramatically reduced because of the high efficiencies. And so they are currently being pursued in markets where you have high fuel cost and you need steady operation. I list some of the barriers. and I list some of the forward-looking solutions. Because of time, I'm going to go on. Kent asked me, or asked us to say a little bit about, so what are you doing about it, Professor? And so this gets pretty technical pretty fast. So, but to honor his request, I give a couple of examples of things we're doing at the University of Maryland to sort of look at some of these barriers in fuel cells and how do we move beyond that. Well, one of the barriers that I mentioned was the fact that precious metals are a critical component of low-temperature fuel cell catalysts. And one of the things, and this is where nanotechnology comes into play, it's everywhere, and yes, we actually try to take advantage of it, is that we can actually, what we've been trying to do is develop nanoparticles that aren't just made of precious metals, but have an internal core of another metal that might be cheaper, in this case gold. And you say, well, isn't gold expensive? Relative to platinum, it's actually pretty cheap. We've also looked at much less expensive metals, and then you put a platinum core around it. And that actually turns out not only to be have less precious metal, actually is a better catalyst. And so we're actually trying to implement this in collaboration with Ballard into an actual fuel cell. Another beautiful, why is it a better catalyst? It actually tolerates impurities such as carbon monoxide much, much better. And so the idea of running a fuel cell, say, directly on ethanol, where you convert the ethanol right there by the fuel cell into hydrogen in a very cheap and easy process, this becomes a feasible possibility in terms of a power plant option for your automobile. On the high temperature fuel cells, we have a lot of work, and just because of time, I won't say too much, but one of the things at universities, our role is to sort of do that sort of fundamental research that kind of looks beyond just trying to build the product for tomorrow. And in this case, solid oxide fuel cells, there's still some material issues in order to optimize them for operability and to think about running them on biomass-derived fuels or on, say, coal gas. And so we're actually trying to do some very fundamental experiments to try and understand what materials will work best if we want to think about using something directly from a biomass gasifier, for example. So my last slide. This is, unfortunately, this is the latest I could find. I thought there was a 2005 version of this, but I couldn't find it. So this is something from Lawrence Livermore National Labs. It's sort of a flow chart of energy usage and energy supply here on the left, and energy usage on the right, and sort of a breakdown of where the resources go. Where do fuel cells and hydrogen, where could they possibly play a role in this picture? And so this is my concluding slide. There is the potential, if we think about centralized power plants, for solid oxide fuel cells to improve the efficiency of this and to reduce this lost energy. That's one area. That's not short term. That's going to be a long-term development effort. And the DOE is sort of spearheading that. Some of us have had concerns about some of the choices in technology that they've chosen, but that's... think about distributed power. If we start to think about putting fuel cells, if you start to think about, say, local hydrogen supply and fuel cells in the residential, you could actually reduce the energy requirements for residential and commercial applications. And also, you could think about cogeneration in industrial plants, and that could actually greatly, particularly reduce this area. But the big one, and the one that I think we all talk about, and that's why I emboldened it, is that can we take off our primary need for petroleum products by switching to a hydrogen-based transportation system, or, as Steve will talk about, maybe a biomass-based transportation system. And I think this is the one that we all dream about, and this is the one that when we talk about the hydrogen economy. And so I'll stop there for...
You want to just run over this?
No, we can do that.
So I discovered the Washington, D.C. traffic grid this morning. So I allotted...
Hydrogen won't help with that.
No, it won't. 95 southbound was a parking lot. The BW Parkway was a parking lot. Baltimore Avenue, US 1 was a parking lot. So I allotted an hour and a half to get here. Should have taken an hour. It took more. So I didn't get this loaded up in advance. Plus I was out of town yesterday.
Today's car-free day in DC.
Yeah, yeah.
Says you notice.
So-
Says you notice. Let's click on the first one. All right. So this was a little bit of a challenge of a talk to put together because I'm not sure of my audience. So anyway, I'm Steve Hutchison, and as I was introduced, I have two roles that I wear. I'm a professor of microbiology at the University of Maryland at the Department of Cell Biology and Molecular Genetics. And based on some technologies developed at the University of Maryland, we're also working through a company that I founded to try to commercialize it. So this is something that fits in very well with Tony's talk. We are obviously putting a lot of CO2 in the atmosphere. It's coming from burning from a fossil fuel. We have a habit of driving an automobile. I don't think that's going to change anytime soon. A lot of people have a large capital investment in their vehicle, but it would be nice to change how we fuel that vehicle. The attractive component of a biofuel alternative is you would still be able to use it with your vehicle. What you're doing in this kind of a scenario is you are taking CO2 out of the atmosphere first, creating some kind of biomass, any kind of plant material. You're basically capturing the energy of sunlight. This creates biomass that then, through a variety of conversion processes, ends up with something called a biofuel. That can be bioethanol, biodiesel, biobutanol, biomethane. And these then can be used to drive an automobile. The nice thing about this is it's a relatively short cycle because you can make this stuff, store it in this form, and then put it into the vehicle. So I'm going to talk about some of these, but because of time, I'm not going to be able to go into all of them in terms of what their options are and what the issues are. But the main thing to realize on this is there's two issues. First of all, it's a materials issue. Number two, it's a biochemistry issue if you go one approach, or a physical chemistry issue if you go another approach. And it's an economic issue because it comes down to, if you're going to use any of these fuels, it has to be economical to drive in a vehicle, and your competition is gasoline. And gasoline has a high energy content. It's relatively easy to get a hold of. There's a large infrastructure to make it, and you have to have something that will compete against it. So some of you, if you follow the news, know about something called corn-based ethanol. This is where you take corn grain. Corn grain is essentially 75% starch. Starch is just simple alpha-1,4-link glucose, not too dissimilar to table sugar. At least that's one component of table sugar. You mill it, you add enzymes to degrade this material, you then throw in some yeast to ferment it, you distill it, you get bioethanol. You get about 89 gallons of ethanol per ton of seed. The translation on a land area basis is about 375 gallons per acre. The problem with this is right now we're taking about 202 billion bushels of corn, using about 130 different facilities, making about 5.5 billion gallons of ethanol. That seems like a lot, but we are currently using about 25% of the U.S. corn crop. Theoretically, if we converted the entire U.S. corn crop to ethanol production, would be about 25 billion gallons. The problems come in is, first of all, this is still 17% of fuel use. We go through 150 billion gallons of gasoline each year. The second problem is a lot of people question the moral ethics of using food to make fuel. And the final thing about corn ethanol is it has a relatively low energy gain. These processes have gotten a lot more efficient over time. You now get about twice as much energy in the ethanol you produce from corn as what you put into it. But in some of the earlier plants, it was basically a wash. It took as much energy to make this ethanol as you got out of it. So the low energy gain was a handicap to this process. When you come through and harvest this material, about 80% of the biomass ends up getting tossed back on the field. If you get outside of the city, you go to any farmland, farmer comes through, runs his combine through the field, pulls out the grain, throws everything back on the field. It's left there to rot, and that is, it gets converted back into CO2. About 50% of this is recoverable for making
energy. You have to return some of it back for sustainable agriculture. That biomass helps for soil quality. So you can only take part of it, but even 50% of this is a lot. Now, if you translate this to realities, this is probably optimistic for wheat. This is in a very high yield area. But if you take the wheat straw, for example, you can produce 100 to 150 gallons per acre. Corn stover, if you take the rest of the plant other than the grain, you can produce about 300 gallons an acre. There are some energy crops out there like switchgrass. This is due to multiple harvests, but you can pull out as much as 800 gallons per acre. There are some energy canes in discussion that can go as high as 1,600 gallons per acre. And you can take forestry byproducts and get as much as 1,000 gallons per acre. If you combine the totality of the biomass in each of these materials, you can easily make 75 billion gallons per year as a renewable resource. So all of this is fine and dandy, but why aren't we doing this? Well, there are two approaches to doing this. One is the enzyme-mediated process. That's where you're taking proteins from an organism, using it to digest the material, and then fermenting it to make yeast. And the other approach is through gasification. Both of them have their sets of problems. I am an enzyme-mediated person, so this is what I know most. All right, so let's back up a little bit, and I can teach you a little bit of chemistry. If you're working with starch, starch is alpha 1,4-link glucose, and occasionally there's a branch at 1,6. That just, if you've got a 6-carbon ring, these are the positions where the bonds are joined, if you're not a chemist. All right, this is chemically simple. It takes roughly 2 to 3 enzymes to digest this. You can make these enzymes for about 2 to 3 cents to do enough to make a gallon of ethanol. When you're talking about biomass, what you're talking about is a plant cell wall. In this plant cell wall, the component that most people are aware of is cellulose. That's what many of you are writing on. Cellulose is beta 1,4-link glucose. The difference between alpha 1,4 and beta 1,4-link glucose is this forms a helix in solution. Therefore, it's easy to attack and digest. This, on the other hand, forms a linear polymer that likes to join up with the next one. So the analogy is that these 1,4 linkages are kind of like bolting it together, and the same thing for the beta, but these bonds in between are kind of like Velcro, sticking them together. So the end result is that when you look at cellulose in a plant cell wall, what you get is microfibrils here. And these microfibrils are about 60 to 75% crystalline. And that's the reason why paper is so durable. Crystalline cellulose has a half-life of 500,000 years. There are stretches that are amorphic, and then if you look at, so that core forms the core, and the amorphic is just individual polymers. Now, surrounding this is going to be something called hemicellulose. This is a different mix of sugars. This coats these so that it protects it from the enzymes that would digest the cellulose. There's also a pectic component that would fit into that. So these purple and sort of chartreuse lines represent polymers cross-linking these cellulose fibrils. And then the whole thing is surrounded by something that's a phenolic compound. That's kind of like a tar. If you extract this stuff, it's functionally equivalent to brown coal. So this is the chemically accurate form of it. This is the stylized version. You've got cellulose surrounded by hemicellulose and pectins formed by lignin. The lignin and hemicellulose form barriers to processing. The cellulose has the fermentable sugars, but it's also crystalline form, which restricts access to enzymes. So to break this down, what most groups are doing is you first take this material, you mill it to a powder, then you extract it in some kind of pretreatment. The most common approach is to take 1% sulfuric acid, cook it at 191 degrees centigrade, which is about 275 degrees Fahrenheit. That means you're at pressure using very expensive alloys. You then blow it to atmospheric pressure to sort of open it up, and then you throw in enzymes. You digest it to its sugars, you ferment it, and you end up with ethanol. Now, your cost factors are going to be, first of all, the feedstock. You've got to make it worth the while of the farmer to harvest this. This pretreatment process costs about $1 a gallon. This part's going to work out to be about 75 cents a gallon if you factor in transportation costs. These enzymes right now, there's no one doing this for less than $1. And then you have the distillation process that's adding in, and probably another $1 on top of that. So if you factor this together, you've got a minimum cost of making this at 375 cents a gallon. That's way too expensive because that's the wholesale cost. Ethanol has about 70% of the energy content of gasoline. You have to do it for a lot less. Another way to look at this is what you're actually doing in this process. In corn, you're taking about 9 kilograms of the material. That's about 20 pounds of the material. You're converting it to sugars, 34 moles. If you're not a chemist, a mole is kind of analogous to a light year in distance. This is a big number. A cup of sugar is roughly a mole of sugar. So you're producing these sugars from that, and then you're making your ethanol to make a gallon of ethanol. The target price is to get this down to $2.50. And I think that's realistic. There are some numbers out there as low as $1.50. It's going to be tough to meet that. The target enzyme cost is to get this down to around 25 cents a gallon. So now that's all the background. Whoops. How do I go back? All right. So to do that, most people are working with enzymes. There's a lot of places you can get enzymes. These are organisms that process biomass. Here's a cow. It eats the biomass. It recovers some of the sugar, although if you've ever looked at a cow pie, it's not very efficient. But there are organisms here in the gut of a cow that will process cellulose. A compost pile is another common place to pull out cellulose-lytic organisms. That is, organisms that can produce enzymes to degrade these materials. Termite gut, if you ever run into that problem, is another good location. Decaying material. One of the more common organisms used to produce this enzyme came from decaying cotton from the South Pacific from World War II, called jungle rot. And it was a fungus that could process cellulose very efficiently. So these are the common varieties, but all of them have intrinsic problems, and all of the economics for producing enzymes from these sources are too expensive. So there's another habitat that is a good source for cellulitic organisms, and that's something that most people wouldn't realize. This is the marine estuary. In fact, this is a salt marsh in the Chesapeake Bay. This particular location, the primary productivity, that is how much organic matter is being generated, is about 10 times higher than anything on land. Yet you see very little organic matter accumulating this material in this area, meaning that there's organisms there that can process that material. An example of that is a bacterium called Sacchariphagus degradans. This came from the Chesapeake Bay. This particular bacterium is a very common variety of bacterium. It's an aerobic marine bacterium, if you're a microbiologist. And what was so unusual about this bacterium is its degradative capabilities. This bacterium could degrade almost any polymer known. If you grow it on an agar plate, the typical medium you'd use for growing bacteria, the colonies sink to the bottom of an agar plate. It will degrade the polymers typically found in other types of algae. It'll grow on crab shells as a sole carbon nitrogen source, but apropos to this discussion is it was able to process very efficiently the polymers of a higher plant cell wall. So what we were able to do is do a very modern approach, which is to get the genome sequence of the organism. That tells us what genes are there, what we can do with those genes. And from those genes, we can identify what the biochemical activities, and what we had is this organism was chock full of enzymes to process cellulosic material. And in fact, if we went through this model, these are enzymes that will degrade the lignin barrier. These are enzymes that will degrade the hemicellulose and pectic layer. These are enzymes that would degrade the cellulose layer. And in fact, because of time I cut out, we can actually go in mechanistically and look at exactly how this organism is processing it. Now the key, and the reason that this is so important, is that this is a one-stop shop to take whole plant material and convert it into its constituent sugars, and this is what you need to be able to ferment that material. So this is a bug grown on the school newspaper. It takes about 24 hours to process it to its constituent sugars. This is a corn leaf, roughly the size of about 3 to 5 centimeters in size. And this takes about 3 to 5 days to produce, and all that's left here is the waxy layer. So this was a pretty unusual capability for this particular, or for any organism really. And so it makes it for a robust source of enzymes to process the material. So to commercialize this, what we've done is we've put together a company where we were developing techniques to make enzymes to process this material to get to this. Right now we're looking at economics of about 25 cents a gallon to make the enzymes for this process. If you're interested, I can tell you more about that. Now, real briefly, I want to mention some of the other approaches. One other approach is gasification. In gasification, what you're doing is you take this material, you put it in a high temperature gasifier, about 1800 degrees Fahrenheit. You make something called syngas. You then use catalytic conversion and refining to get to ethanol. This is an alternative approach, and there are a number of companies out there that are trying this approach. The main problem with this approach is this is a really dirty gas. If you've burned a fire in your fireplace, periodically you got to have somebody come through and clean out your fireplace because you're putting tars into that material. But the problem with those tars is that they gunk up the catalysts, and those catalysts, as Greg was talking about, can be really expensive because usually they're made out of some exotic metal. So this approach is being tried by several companies. It's not clear whether it will approach. There are other alternatives. You can make biodiesel. Here's an example where you're taking soybean, you're converting it to soybean oil. The problem is you're only using 4% of the original biomass. You then use lye and methanol to refine it into bioethanol. The problem with biodiesel is that if you take soybean, you can produce about 48 gallons per acre. Right now, the U.S. soybean would yield about 5 billion gallons of biodiesel. If you wanted to meet 50% of fuel needs, you'd have to plant 2.5 million square miles of soybean, and that translates to 2/3 of the square miles of the U.S. at the present form. If you can grow peanuts all over the place, you get a little better yield. There's not much grown, however. To meet 50% of need is 1 million square miles. The prize winner is down here. There's some algae. Can produce as much as 7,000 gallons per acre. That would translate for 50% need of about 16,700 square miles. That's roughly equivalent to the area combined of Vermont and New Hampshire, or about 2/3 of Lake Michigan. And that's the square mileage you'd have to convert into algal growth to do that process. So the other approach that's being proposed is to make a fuel that has a little higher energy content. That's called biobutanol. Again, it's a very similar process. You're going to use enzymes that digest it, take the sugars, ferment it into biobutanol in this case. The problem with biobutanol is it's biotoxic, so that you only produce a small amount of it. Your economics in terms of your flow is and distillation process makes this right now a very difficult process. All right, and the last thing I'll make mention of is in Europe, this is used extensively. What you do is you throw in your biomass. You have a mixture of bacteria in here, no oxygen present. What you produce is methane gas, and then they use a cogeneration site where they convert the methane gas into electricity at that site. It's something that's not being explored. It's just starting to be explored, actually, in the U.S., but it is another option for processing biomass. The rate limiting step here is still conversion of cellulosic material. All right. So with that, I will stop and we'll move on.
Hi, I'm Tim Golden. I'm a research scholar at the Center for International Security Studies at Maryland in the School of Public Policy. And I'm going to look at some of the broader geopolitical issues associated with some of the shifts in energy technology that might be needed, and particularly look at the role of nuclear energy, which I think I'll argue almost certainly needs to play a major role if we're going to get through all this. So first off, the world energy supply really needs to be radically transformed over the next 50 to 100 years, and that needs to start now. One reason that we've been looking at in the Center for International Security Studies is that equitable development seems to be really essential for keeping the world a safe and happy place. The developing world has been kind of developing for a long time. In many cases, has not been developing as fast as we would have liked. And as we move into a world with asymmetric threats, where terrorism is a concern, it really seems increasingly the case that it's not just an equity argument. The poor not only shouldn't have to be poor, they're really not willing to remain poor. And that if the world is going to prosper environmentally and be a safe, sustainable place, we really need to be sure that any solution that we propose is compatible with the development of the less developed parts of the world. And there are an awful lot of factors that go into looking at the total mix of technologies that would be required to make this happen. But most of the ways you slice it, most of the ways we can make it shake out, we really need to expand global energy supply by a factor of 4 or 5 between now and 2050. Now, that's a big expansion in global energy supply. And this assumes much more rapid increases in efficiency than we've ever seen before. Realistic, but I'm not ignoring efficiency here. Even with gains in efficiency, we still need really a lot more power if the developing world is going to develop over the next 50 to 100 years. So if we're going to have this great increase in energy supply, we're going to need to, but yet we can't break the global carbon budget. We really need to reduce our output of CO2 substantially, starting soon. So to make this math work out, you really need to move the global energy system from being about 15% carbon-free sources, very rough overview numbers, to between 50 and 80% carbon-free. That's a big transformation. Carbon-free energy needs to grow by a factor of 5 to 15 over the next 50 years. And 3 to 5% per year is kind of the middle of that range over that whole period. 3 to 5% per year, that's fast. That's a rapid changeover. However, there's hope that it can be done. Looking again at the big historical picture, in the past it's taken about 50 years for sources to come online. The big shift from firewood to coal happened between 1850 and 1900. That's the time it took to go from coal to go from about 10% of supply to about 60%. From coal, oil, and gas. Again, rough, but for oil and gas were not really major energy sources in 1925. 1975, they really made up a substantial amount of the energy used in a lot of sectors. About a 50-year turnover. Well, to go from fossil fuel to carbon-free sources, it would be nice if we could do it between 2000 and 2050. Maybe we should move that bar to 2010 to 2060. But it seems plausible that this major transformation of world energy supply can be done in this kind of time frame. It's happened before. Once the market kind of gets a hold of the technologies, the shift can happen fairly abruptly. But we really need to get moving here. Prices, the market signals aren't necessarily going to force this to happen. The market isn't necessarily taking into account damage that will occur 100 years from now. These are policy issues, and we need to probably intervene and nudge the market, help the market to push these technologies to be adopted. Looking at the big picture here, we've identified, and there are various studies that are parallel to this, but this is pulled from a piece that our esteemed dean at the School of Public Policy, Steve Fetter, did. It's comparable to a study that Pakula Sakalo did in Scientific American in 2004, but there were some slightly different conclusions. Identify 7 different sources that are potential contributors in the carbon-free area. Hydroelectric produces a fair amount of power now. The problem is most of the good sources are taken. There aren't that many more rivers to dam. There are problems with big dams. It'll grow Some, but not hugely. Maybe double. Geothermal. There is some use of geothermal now. That has the potential to grow. There's a lot of debate right now as to what the build-out potential is for geothermal. There's a lot of energy trapped in the earth, but extracting it in a cost-effective way is really challenging, and we're not confident that it can become a huge contributor. The ocean, there's an awful lot of energy in waves, in thermal gradients, difference in temperature between surface and below. And that certainly has the potential to grow, but there are various technical limitations. We don't think it can contribute a major percentage of this increase that's needed. So we're left now with, I'll leave fission out for the moment. Biomass, we've talked about, is capable of producing really a lot of power, probably most of what we need for transportation. But when you look at potential for biomass against the total power needs of global society, it doesn't seem it can do the whole thing. It can be a big player, but probably not the whole thing. Solar, small contributor now. There's a lot of sun falls on the planet every day, but capturing that cost effectively, challenging. It can definitely grow. It can definitely be parts of processes for creating hydrogen, but probably can't be the whole solution either. Wind, hot thing now. Nice return on your investment there, but it's only useful in really windy places. It's intermittent. It doesn't work well at night when the wind isn't blowing. It can be a player. We're thinking 20 to 50 exajoules of energy per year is the potential over the next 50 years. Decarbonized fossil, to grab the carbon from fossil fuels and sequester them either in geological repositories or possibly in the very deep ocean. This is a technology that we were quite pessimistic on a while ago, but some very good new research is being done. It does look like it's going to be possible to keep using coal, natural gas, and capture the carbon. However, that is still very much under development. Hot area of research. I'm not wildly expert on it right now. We think it can be a player, but again, not the whole thing. Which leaves us with nuclear fission. Good old nuclear power that we're accustomed to. This is deployed on a fairly large scale today, has the potential to grow to be quite a bit bigger. It's the one of these technologies that is really in use in a large way today. And we basically, long and short of it, we believe, looking at the big picture, this has to be a part of a sustainable strategy. Many of us in the environmental policy world were not big fans of nuclear energy previously. It still has problems, but climate change is a huge problem, larger problem, a longer-term problem, harder problem to manage, we think, in many ways at this point. So if we add up all of these projections for their energy potential, based on our estimates, come up with about 600 exajoules of energy that they could produce per year. We think we need between 300 and 900 exajoules. Well, so it might or might not be possible to do it without fission. But that's, of course, only if everything goes well. If we end up at the high end of all those ranges. If we end up at the low end, well, we might end up with 350 exajoules from non-nuclear sources. We need 300 to 900. It's pretty unlikely that we're going to get it done if we end up at the low end. So this 70 to 220 exajoules from fission seems to be critical to achieving the target. We know how to do it. And it's, unlike many of the other sources, is really well suited to provide base load energy. Works great at night, very predictable. Once you build the plant, you pretty much know what you're going to get from it. So it's a nice part of a mix with more volatile sources. There are problems with fission, though. Accidents, waste, and the area that we are more focused on is weapon proliferation. You can make bombs with many of the same processes that you use to make nuclear energy. All these are greatly magnified when nuclear fission is increased by a factor of 6 to 8, as really might be required. Some credible estimates have thought that we could get there with a doubling. It's possible, but we're not happy with some of the assumptions involved, that every unit of nuclear energy is replacing the dirtiest forms of coal, for instance. Nuclear would probably be crowding out some natural gas, some things that are less carbon intensive. We think an increase of 6 to 8 is realistic and something we need to plan for. And much of this will be in the developing world. This won't be in the U.S. and France and Britain. This will be in India, in Pakistan, in Indonesia, in places that don't have the long records of safety culture, where we don't perhaps feel secure about their nuclear weapons intentions. But we need them to be players. We need them to use this technology. We all have to pull together to reduce carbon emissions. So while these problems aren't to be dismissed, we have to deal with them. Climate change is certain. Many of these are uncertainties. Climate change, we really know an awful lot about how it's going to play out, and it's not good. We have to act. So we need some new approaches. We need to maintain operational safety in the face of many more plants located in developing places. It means basically we need safer plant designs. We certainly can't have Chernobyl-style designs. Arguably, we can't even have the current generation of light water reactors that we use today. These really require good engineering, very careful management, and they still have problems from time to time. Safer reactors would be a very good thing. We need to manage the waste stream. There may be ways to rethink the nuclear fuel cycle so that we produce less waste that's easier to store. Currently, the economical thing and the safe thing is to use a once-through fuel cycle, where we take raw uranium, refine it slightly, use it, and store it. Throw it away. There is a lot of uranium. We can do that for quite a while. The problem with reprocessing, where you use the same fuel over and over again, is you end up with plutonium if you do it the easy way. You end up with the easy way, which is still hard, but the way it's generally done, you end up with bomb-grade plutonium. And you really don't want bomb-grade plutonium plentifully spread around the world. And containing the threat of nuclear weapons proliferation because of reprocessing is a big deal, and something that we can't leave out of the equation. So the IAEA Director General Verity has proposed a plan that would restrict all processing of weapons-grade materials to facilities under multinational control, convert all highly enriched uranium facilities, bomb-grade, they use bomb-grade stuff as fuel, to low enriched, which you can't make bombs from. Although you can still make dirty bombs. You can still spread it around and make a big mess, but you can't make nuclear detonations with low enriched uranium. Would provide reliable access to low enriched uranium for countries that were complying with the protocol, and advocate the creation of multilateral agreements to dispose of waste. It doesn't necessarily make sense for every using country to dispose of the waste within its own borders. Some places are just better suited than others. Some governments are better able to keep track of these things than others. This would go a long way toward containing weapons proliferation, but it would do less to address accidents and diversion of non-grade material, using a dirty bomb. It's also, well, yeah, so it addresses parts. It addresses the thing that IAEA is most concerned about, which is proliferation, and is a framework that might really provide a foundation for expansion that's safe in terms of proliferation. I'm trying to really move quickly through this because I know we're running a bit long. So we think that's a good start, and that kind of deep international cooperation is probably necessary to expand this power source on the scale it needs to be expanded on. In the long term, we might think even beyond that, and a design that we've commissioned a couple of papers on and think is really promising is a hub and spoke design based on the notion of international energy parks, where there would be a few places, maybe a half dozen, maybe a couple more, all under international control, that would do all of the processing of nuclear fuel for the planet. They could be done under tight security, carefully designed international management. All handling of nuclear materials would happen there. And they produce long-life sealed core reactors. There are a couple of designs that are being worked on in a number of places. Some work going on at Maryland on this also. They'll basically be treated as nuclear batteries, where you'd end up with a thing that could be transported on a large truck, certainly easily on a barge, that would be loaded with a nuclear core, probably using a molten lead cooled design as the designs that are most popular in the engineering circles, as far as I know at this point. Perhaps also pebble bed reactors could be done this way. Material would be put in, sealed. The nice thing about the molten lead core is that the material is encased in solid lead when it's not operating, and in molten lead when it is operating. It's both pretty hard to tamper with. They could be designed in a way where if someone did try to open it, it would be detectable by international authorities. They'd be moved from the park to the place where they would be used and run for 15 to 20 years, probably with fairly little active management. They would just produce power, and at the end of the time be returned for refueling and recycling. And now to make this work and to make it attractive to nations, particularly nations that don't currently have nuclear programs, there would need to be a certain guarantee of access. That if a country is being reasonably compliant with a set of minimal standards, they have access to this technology at a price that they can afford, and that they don't have to worry about being cut off. There would have to be a protocol that really makes them confident that they're going to be able to get the power that they need. To get there will require technical, institutional, and political progress, but these problems are both of climate change and of nuclear proliferation are large enough that substantial efforts need to be made. Just scaling up our current system, or even a easy to foresee descendant of our current system, where certain countries have this technology, others don't. We do what we can to keep new countries from getting it. We essentially trust the countries that have nuclear technology to use it appropriately. This really doesn't scale up. We're really quite concerned that we need to think now about establishing the institutional frameworks to make a scheme along these lines work in the long term. I was afraid this would be illegible, so I didn't put too much, but I do have color. I can't do color. This is a map of dividing the world somewhat arbitrarily. There's some thought behind this, into 6 zones that would produce the batteries. Different mixes of in-place reactors, the kind of reactors we're used to, and batteries for different areas. In North America, where we have an established grid and an established supply system already, more reactors would make sense, fewer batteries. In Africa, probably South Africa, there are a few places where it might make sense to do big installations, but the battery approach would probably be much more feasible. And I guess the critical take-home, though, is because there's a long lead time on designing these reactors, building them. We need to make things happen over the next 50 years. And the reactors that are being designed now will be coming online 20 years from now, and will run for 20 years. So the future is now. And if we're going to change the institutional structures and the technologies to take into account both things that the market will do, efficiency, but also things the market won't do, security, and preventing climate change itself to a large extent, we really need to be thinking about those things up front, because we have to live with the decisions through the period that we need to reap the results. Thanks.
Quite an education, enormously rich and presentation, and still just a hint of what is going on at the University of Maryland. Now, let's open it up for questions, and as you ask a question, please introduce yourself and give us your affiliation. The gentleman there, and then the gentleman. Is that Dan Lamote? Oh, Dan, welcome. The former board member of the council, Dan Lamote.
Hi, I'm Alan Hoffman with the U.S. Department of Energy, Office of Energy Efficiency and Renewable Energy. I heard a lot of discussion of energy sources, supply. I heard almost nothing about efficiency. And there were a few words that said, yeah, we recognize efficiency has to be there, but my personal opinion is it has to be the first priority of energy policy. I don't hear you addressing that issue. Is that a concern to your center?
Greg, maybe I should take that one.
Yes, Alan, I think yes, there are researchers on campus that are within our center that are addressing energy efficiency. One of the bigger players is Reinhard Rademacher, and in fact, these types of problems are often addressed on a case-by-case basis. One of the things that Reinhard's does is he has an industrial center that provides advice and implementation strategies for improving efficiency of industrial processes.
You have one person?
No, he actually has a team. He's the director of this. It's a Mid-Atlantic CHP Application Center. In fact, it's funded in part by the DOE as well as by the states that are involved. And you are correct, though, that I think it doesn't often get the attention that it needs. In part, I think you start to talk to academics, we tend to like to. Sometimes we like to look beyond what's right in front of our nose. I will admit that I do that sometimes myself. I think efficiency has to be a part of the answer, but I think as Tony's talk clearly pointed out, it doesn't address the problems regarding source and emissions that we need to address as well.
I want to pick up on this. It's actually, for the Joint Institute, it's actually quite a big deal for us, and because for a couple of reasons. And one is that all of the work that we've done with the integrated models embodies a whole host of either assumptions or actual modeling on changes in efficiency, both at end-use efficiency, both at national scales but increasingly at regional scales. And so one of the areas that we're actively pursuing now with both government and corporate partners is a much more comprehensive sort of deep dive into end-use efficiency issues and how we can better represent that in the models. We've just finished some work, for example, for the California Energy Commission that takes a much more substantial look at end-use efficiency issues, particularly in that particular case in the building sector. But the same thing occurs in all sectors. One of our, and this has taken on more of an international dimension for us as well, one of our researchers is on her way to China today, maybe tomorrow, to do some work explore some work with partners there on both on end-use efficiencies and on combined heat and power generation. And so this is an area where we're actually beginning to expand our efforts. The fact is that most of the near-term gains, by near-term I mean over the next 10 to 20 years, are actually much more likely to come out of gains in end-use efficiency and, in a sense, than the relative change in emissions than they are in power generation, simply because of the length of time that it takes to turn over energy infrastructure. Nobody in the U.S. anyway, buys a new car every 3 years anymore. The life of the transportation fleet is extended out to 10 to 12 to 15 years. Power plants have a 30 to 40 year life spans. We haven't built a new nuclear plant since, what was the last one after Seabrook? I don't know, Diablo Canyon or somewhere. We haven't built a new one since I was in college. And even though there are now lots of applications in the pipeline, those plants are lasting, 30 plus years. I mean, it just will take time to turn that infrastructure over. In the meanwhile, we have to make gains quickly, and it's quite clear that improvements in end-use efficiency have a major role to play. Big challenge is, why aren't we using the existing gains in technological options available to us right now, why haven't those penetrated more thoroughly than they have? And I think, there's lots of after the fact discussion of that, and my sense is relatively little actual understanding of that. So that will be a challenge.
Dan, before we come to you, I wonder if just wanted to yield to the chairman for a question.
No, I just have a question that, with your studies, in energy sources, I'm sure that this is being replicated in other universities throughout the country, other labs. Is there a coordination of these studies with the Department of Energy or elsewhere where there's not a great deal of overlapping?
You want to start from the standpoint of the center?
Yes. Certainly, I think, yes, we, as academics, we have our conferences, we have our meetings where we collaborate. Almost all the research that I personally participate in, with maybe one or two exceptions, has interactions with other institutions. In fact, that tends to be more and more the model of funding from government agencies, is much more funding multi-university efforts. There's certainly cross-fertilization of both ideas and through collaboration as well as through our meetings. I think I don't think it's as centralized maybe as it should be, but sometimes maybe that if it's too centralized, maybe you tend to crowd out some of the more creative ideas that would come to the fore if time was given to let them germinate. So I'm not sure that it's optimized, but I'm not sure what an optimal system looks like.
Does the Department of Energy become involved?
I think that the national labs and the Department of Energy are the leaders in sort of guiding a lot of the sort of big programs and as academic institutions, we certainly have to respond to that because they're a source of a lot of our research dollars. I think they are not the only funders of energy. The Department of Defense actually is also a big funder of energy research efforts.
Dan?
Hi, my name is Daniel Mona. I'm a former member of the Woodrow Wilson Council. I have a couple of questions. First of all, I want to thank you for your presentation. I thought it was great. It's a very important topic, and you made it you kept it very non-technical for me. It was quite helpful. And if you indulge me, I'll ask all my questions right now all at once. One is, when we mentioned the 4 to 5 times in 50 years of energy for the worldwide, I'd like to know what was the baseline in terms of energy per capita that was used for that, and was that on a curve, or is it sort of equal for around the world? Another part is in terms of the cost, the total cost for implementing most of this technology, both for the United States on a global basis. Has there been a study in terms of what would the pain that we would have to either give up in terms of taxes, tariff, or whatever, to be able to pay for this technology, and what would it translate in terms of GNP, world GNP, reduction of world GNP for the next few, several decades to achieve that technology. And the last question is in terms of, is there a component of urban planning in your group to look at conservation? Because it's been said that you can save a whole lot more and gain more time in the whole process with intelligent design. Thank you.
Well, the technical question on the.
Please be sure to speak into the mic.
I am trying to remember exactly how the 4 to 5 time estimate was calculated. I was involved with that calculation. That wasn't really my calculation. I know that we projected increases in efficiency about double what we've seen in recent decades, and I believe the thought was to bring, by the end of the 50 years, to bring the developing, the parts of the world that are using very little energy now, up to using not quite comparable energy to the U.S. and Europe, but somewhere in the same, more than half. And that's, of course, with the U.S. and Europe using progressively less over that time. I would be guessing if I tried to give you more precise parameters than that, but that was the basic notion. And the last question, what was the last question? I felt like
Urban design.
Oh, urban design. I'm actually a planner by profession before I came back to get my PhD, and we'll actually be presenting at a conference on Monday using the light you can see from space to try to understand urban sprawl in the U.S. and Europe. It's something that I'm personally very interested in, and I'm probably not as well tied into the other parts of the campus as I might be, but it's something that I'm with the National Center for Smart Growth isn't formally part of UMERC, I don't think, but there's a lot of overlap between people who are part of UMERC and them in the form of me and probably among others.
I could also address at least a couple of those issues. Many of the integrated modeling groups that have worked, for example, on the IPCC, Intergovernmental Panel for Climate Change projections and scenarios for the 21st century, at least in the last couple of rounds of IPCC, those scenarios have been constructed in such a way that what they're exploring is a future where there is convergence of economic growth in both the developed and developing worlds. And so they have built into them a set of assumptions about increased consumption and economic well-being in the developing world. I wouldn't even hazard a guess as to exactly how that plays out in terms of numbers, in terms of energy use, but typically what one sees in those kinds of scenarios are increasing per capita uses of energy in the developing world, even as efficiency increases and so on. And the relative contribution of the developed world gets smaller. Not surprising, I think. Those are in part continuations of trends that we're seeing right now. The issue of costs, IPCC has looked at costs any number of times globally in terms of what it would take to achieve stabilization levels, what fractions of global GDP it would take. They typically come up with answers that over the century it's maybe a few percent, which is this notion that these changes, while large, would be somehow crippling to world economic growth is not consistent with what the current published literature suggests. It really suggests something quite different. It's not to say the cost is zero. The costs, in a sense, capital costs and investments are large. The current economics doesn't favor making a lot of those investments, and so this is an area where both markets need to be responsive, but in order to achieve those kinds of changes, it will require policy developments as well. We don't have your last question about urban design. We don't have that particular expertise in our institute. I happen to live in North Arlington, and our offices are in College Park. If there were to be urban design, it would be nice if it were to be intelligent. That's about all I can say on
The
that.
gentleman there and then the lady here.
Chuck Weiss from Georgetown School of Foreign Service. Two questions. On the nuclear side, how are you going to get countries to accept a system in which a multinationally controlled energy park controls the supply of a critical amount of your electric power, and it's only available to participating countries with good behavior? So they get to choose who's a good behavior and who's not good behavior. The World Bank has enough trouble with conditionality, and that's only money. For Professor Hutchinson, I wanted to ask a technical question. These high-performance grasses, the tropical grass and the switchgrass, realistically, if they became a major source of biomass, raw material for biomass fuel, is it reasonable to expect that they could be grown on land that is now not considered agricultural, or would they, for economic and for techno-economic reasons, probably displace existing agricultural land?
Which question do you want to do first?
You pick.
I can be quick.
Okay.
I think the essence of any kind of a hub and spoke arrangement, or any kind of a internationalization of reprocessing arrangement, would have to rely as heavily on guarantees of accessibility, or more heavily on guarantees of accessibility, than it would on conditionality. There might have to be some basic conditionalities in order to get nuclear states to agree to the deal, but there would have to be an awful lot of, the standards would have to be fairly low, and the guarantees of access would have to be awfully strong for the non-nuclear states to agree to their end. And there's a negotiation that can happen there, but we think a balance can be struck. But it would mean, in in today's world, North Korea would have access. Now they wouldn't have access to reprocessing, but you'd have to be in an awfully bad state, I suspect, to run afoul of the rules, and the rules would basically guarantee, even if nobody likes you, you still get to buy at the standard price. That would have to be decided in some detail.
Okay. So the question really is...
Can you please speak into the microphone?
No, sure. So the question is how much would an energy crop displace food production?
Yes, if you use one of these grasses that isn't now.
So the advantage of the grasses is they will grow in marginal soils and areas that primarily are not in productivity. You're not going to see the same levels of productivity if you took prime land, farmland, into production. The goal is to come through, and it'll probably be a combination of some displacement of a food crop, but we're still producing some excess food. And some use of marginal lands that currently are not in production. Exact numbers, I don't know at this time.
Can I chime in on this question? Because a lot of it is not so much the biology of where they will grow, it's the economic response of the farmers, is what will they do. The U.S. this year will have a corn crop that is the largest in any year since the Second World War. It's been reported a couple of times in the newspapers, and most recently is, I think now, actually the official USDA projection. That's an extraordinary change in the space of about 18 months. Nobody predicted that. The agricultural systems are extraordinarily responsive to these kinds of price signals. So one of the big challenges is not so much what are the plants capable of doing and where are we capable of getting reasonable yields, but why would any farmer, a farmer will have a choice of where that crop goes, and imagining that farmers will forego extremely profitable energy crops in order to plant soybean seems to me to be quite unlikely. We've actually, in a lot of this, we started looking at biofuels, as have all of the other integrated assessment groups. And a lot of it depends on what assumptions you put in. For experiments that model experiments that constrain the models to always produce enough food for the doubling in food supply that we'll probably need by mid-century, you tend to then displace energy crops into marginal lands. If you don't put that constraint in, then you absolutely get a competition for high-yielding land between energy crops and food. And where that competition plays out, I don't think we understand very well globally at this point. It is very likely that we will continue to produce excess food, and it then becomes a question of distribution as to whether you run into food security problems. The bigger challenge, I think, is whether or not we put a price on carbon for all sources of CO2 to the atmosphere. If you leave biological carbon out, which is essentially the same as saying there's no price on deforestation, then and you really like biofuels, then what the model suggests is that you will deforest the earth as quickly as humanly possible in order to produce energy crops. We all get that result. It apparently is a very robust result.
It's an experimental result. happening with the palm oil plantations.
And it has in this case the environmental misfortune of appearing to be true because it apparently is describing something that is actually going on in today's world. And one of the policy lessons for that is that if you're going to put a price on carbon, on essentially excess carbon, you'd better put a price on all the sources of excess carbon, and not just the fossil fuel sources.
And I can still follow up on that one. You made mention of the large corn production this year, and then a lot of the driving force for that was corn right now is at a historic high for its price. I think it's running about $4 a bushel. That gave each farmer about a 33% increase in yield per acre for income, and that's a big driving force. One of the problems in biomass conversion is actually the economics of the process in terms of the price of biomass per acre, per ton that the farmer would be getting is about $50 a ton. That's most of the estimates there. And if you've got a wheat crop, you're harvesting, maybe a ton and a half per acre that you can take out. Now it becomes a question to the farmer: is that going to be worth my while to come through and harvest that material? And where am I going to get the best bang for the buck? So right now, corn we can grow really well. There's enough acreage out there. There are new varieties coming up that are going to have increased productivity. It's likely that corn's going to be grown on a lot of acreage, but mostly for ethanol production, meaning at least an increasing percentage. Right now, they're predicting that corn ethanol will go to 15 billion gallons a year, so 3 times the current production. And we're going to have to correspondingly increase the amount of corn production to be able to meet that need, or put up with increasing food prices, because we're already seeing that at the grocery store, just at $4 a bushel.
Please, just get a microphone coming here. Please introduce yourself.
Good morning. My name is Maureen Coates. I was the Acting Assistant Secretary of the Air Force for Installations, Environment, and Logistics. So we had a pretty significant energy use, among other things. My question, though, goes a little bit more to the sort of larger picture. I had a not inconsiderable number of engineers working for me, and I was always impressed with how quickly they could go to tactical and completely bypass strategic. It strikes me that we, and Mr. Goulden, I think you hit on this a little bit, there are already major historic, sociological, political, and economic trends, activities associated with energy availability, energy's relation to poverty elimination, energy deployment mechanisms, relative types of deployment mechanisms. It's not all fungible. There's base load, there's urban, and I'm glad to hear you're a planner, because those were the thoughts going through my mind. How are we talking about future energy system planning and design relative to how we think we want to use the planet and accommodate a lot of people's future needs, such that we are going back and reconstituting some information such that we can maybe give ourselves some guideposts, like base load's a good idea, base load's a bad idea. Base load is useful under these circumstances, base load's not useful under these circumstances. Therefore, here's how we should be investing in base load that doesn't make large amounts of carbon or other uses of the atmospheric arena, or we shouldn't. I mean, we're kind of diving right into these distributed transportation technology constructs without giving ourselves some idea. Improving transportation fuels, to me, doesn't necessarily get you mass transit improvements. Where's maglev? Where's the features for what we want this energy to go do for ourselves? What are the issues for women and poor people? And what kind of energy do women need? Who needs night school the most? Therefore, they need to be in a place where the lights are on till 12 o'clock at night, like most of us took advantage of. I mean, does your institute cover any of this in terms of giving yourselves some thought parameters for how all of this other examination will take place?
I'll start. I mean, a lot of when we use the integrated model system to try to look at energy systems and potential futures. In fact, what many of these are economic-based models. And in fact, what they actually model are the production and use of energy-related services. And so for transportation, for example, what the models actually generate are the equivalent of services in transportation. They're not attempting to model the all of the distribution of the fleet. And part of why that's important is that it enables us to then ask the question, where would different technologies or different redesigns actually affect the overall energy system, and how might that play out in the future? So to give you just one example, when we started having enough data to be able to look at the issues of plug-in hybrid vehicles as one of many technological improvements in the transportation system, it turns out that many of the model experiments want to expand plug-in hybrids tremendously. But that only works if there's a way to produce electricity in essentially a carbon-free way, either sequestering carbon from continued fossil fuel sources or alternative carbon-free energy production. And in fact, what the models want to do is electrify everything, because there are many more options for reduced carbon electricity generation as a power source than almost anything else.
But I'll be honest with you, my question really went to, and I'm very familiar with modeling. Modeling is, let me take today and imagine tomorrow, as opposed to, it's some version of empirical study, where it's, let me look at what's been happening for 200 years and figure out whether one is better than the other.
This is not blue sky calculation. This is empirically based modeling based on what we know today about either the performance of technologies or how the system actually works in today's world, what is reasonable for tomorrow. We don't make a pretense that we're predicting what the future will hold. What we're trying to do is see how the different aspects of the system actually interact with each other, so that we can see, to the extent that we understand it, so that we can see where some of the decision points actually are. It's a very strategic view of how one ought to be thinking about what the future holds for energy production and use and the services that it generates. Because it's clear that it's absolutely crucial for where not only our society, but where societies around the globe are actually going to go.
We run past our time, but I did promise the ambassador from the Department of Energy a single last question, and I just beg him to make it brief. So I promise to get people.
The question will be brief. I hope the answers will be brief too.
You need to use the microphone.
Thank you.
One issue that touches, I think, on all the speakers' areas of interest has not been really explicitly mentioned. That's water. I mean, the hydrogen people have to worry about, water is a source of hydrogen. Obviously, the biomass people have to worry about it. Global climate change is going to affect water distribution around the world, and if you're going to cool a nuclear power plant, you better have some water. And that's already a problem in this country. To what extent are you guys worrying about water issues?
Major research push for us. It's not so clear to get all those billions of gallons of biomass where all the water is going to come from. And we're working, it's an active research topic on trying to build water and, frankly, nitrogen and fertilizer use into our system models. Those are two huge issues.
So a lot of the biomass conversion plants actually are incorporating in recycling on the water, so that to minimize their water footprint. Some of the systems that we're looking at for enzyme production, actually recycling the water is a major cost containment factor. So there's some water use, but if you look at where, let's say, corn ethanol plants are situated right now, they're not in areas that use a lot of water directly. They're actually their waste treatment for water is not as large as you might think, and what wastewater they're producing goes right back into the plant. So,
one of CISM's major focus really is understanding civil conflict more generally, and climate change being an aspect, trying to figure it out. But water, of course, conflicts over water, and particularly over shifting water patterns, is absolutely a huge issue. And our focus is usually trying to understand really how that relates to conflict. But of course, anytime you take what people own now and shift those patterns as climate change does, it's a big driver, and it's not well understood by anyone, but we're trying.
Let me just make a plug for the Wilson Center's Environmental Change and Security Project, which does a lot of thinking about water related to conflict, related actually to the potential for negotiations over water leading to a more positive outcome.